Okay, so we've got our last lesson of our current unit. Actually, we were in Chapter 6. We have to jump over to Section 9.1. Most textbooks actually include this lesson with the volume chapter as well. It's just a slight adjustment. Today, we're finding arc length. You can see that's our learning target. So here's a big criteria. If f is smooth on the interval, if f prime, the derivative, is continuous. In other words, f is not only continuous, but there are no corners, there are no cusps. That means that your derivative is always defined. If that is true, if your curve is smooth, you can find arc length, the distance that you would travel on a curve between 2 points. So take a look at this picture right here. You could begin at a point A, you could end at a point B, and very clearly as you look at this, this is not a straight line connecting A to B, but you could say, I wonder what distance, what the arc length would be traveling from point A to point B. Well, from the context of what we've had, we can say, look, just start labeling points x comma y, like a comma f of a. A is your first point. The end point is b, so you'd have b and f of b. And let's just break this x interval into sub-intervals. Break it into a whole bunch of tiny pieces. By the way, that should begin to start to look very, very common to what we've been doing all unit. You know, whether it was chopping things into little rectangles, like we were dealing with work the other day, where we were breaking the distance that a particle would be measured for work. We broke it into tiny little distances. That's what we're doing here. We're going to, say, look, take this curve and all of a sudden just break our x's, like we have an x1 and an x2. That would correspond to 2 points on the curve. Guys, here's what's really going on. Let's just say that we are looking at 2 just general points on that subinterval, like we have from x sub k minus 1 to x sub k, and you can see that we'd have x sub k, f of x sub k, we'd have f of x sub k minus 1 for the x sub k minus 1 as well. We can go back to the distance formula. See, right now I think we could all agree that even though the distance formula would be measuring the length of that segment connecting those points, if these two x values were super, super close together, even though that would still have a curve, that segment would be amazingly close to the real distance between them. So what we can do real quickly is work out that distance formula right here. So we'd have x2 minus x1, we'd have x sub k minus x sub k minus 1, and square that. We'd have f of x sub k minus f of x sub k minus 1, and we'd square that. Now right now that can seem rather obscure. Let's remember the mean value theorem though. That seems to be so disconnected to what we've got. If f is continuous on the closed interval and differentiable, we'd say that f prime of c was equal to f of b minus f of a all over b minus a. That's really your y2 minus y1 all over x2 minus x1. Guys, that's what the distance formula has. It's a y2 minus y1 over x2 minus x1. So what are we getting at? We're saying that, look, if I wanted to solve for the y2 minus y1, if I wanted to just solve for that, I'd have f of x sub k minus f of x sub k minus 1. And we'd say that's equal to f prime of c times the x sub k minus x sub k plus 1. Why do we bring that up? Well, what we can do is we can also point out that right here, delta x is the change in the x right there. So look, what we have is this much. If I were to say, look right here in green, that expression could be changed to f prime times x sub k minus k sub 1. But the x sub k minus x sub k plus 1 is delta x. So this x2 minus x1 is your delta x as well. So all of a sudden, that distance formula could be rewritten in that form. And you're going to notice that both of those expressions have a delta x squared. We could factor out that delta x squared, take the square root of it, and then, that's that intermediary step right here. Once we pull that delta x out, we would have this right here. Now, believe it or not, what you're seeing is if we made that a Riemann sum, that's how we get the arc length. So I don't want you to just see this formula and never ever have any realization where that could come from. But this right here in the red box is what you have to have memorized. If you want to find arc length, the arc length is the integral from a to b of the square root of 1 plus the derivative of x squared. So imagine what you can now do in light of what we're seeing right here. We can say here's a curve, and you're given some beginning point and an end point, a point A and a point B. And they're saying, hey, find that distance on the curve, find the arc length. Well, what you're going to have to do is take a derivative. Here's f of x is 2/3 x to the 2/3. Help me out. What's that derivative, guys? What do we get? 4/9. And what's my new power here? Negative 1/3. I've got to subtract 1. Now, in that red box, guys, the arc length is going to be integrated from your first x value, which is 1, that's your a, little a, to your ending x value, which is 8, that's your b. Yes?
If it was x equals 2 y, is the power 2
Well, yeah, if x is equal to something, that's on the flip side. That's our last example. We'll see that in a moment. It's very much a similar setup. For right now, though, when you have y equals the function of x, we're using that red box, and we'll be able to move from there. Yes?
So for the first red box, what exactly are we?
We're finding the distance between one point and another on that curve. This is the arc length formula, right? You're finding how far it is, how far, like a little bug would walk, going from one point.
It's like a piece of rope.
Yep, exactly. It's like saying, here's a piece of rope right here. Stretch it out. How long is that rope? What distance did we really just travel?
And would that be an exact answer or?
Well, if you worked out the integral itself exactly, then you'd get the exact answer. If you're using your calculator, then you're getting a pretty good estimate. Now, what you're going to see is, at this stage, most of these integrals are very, very complicated looking. You could see as we have this integral right here, trying to do a u substitution would not help you. You don't have enough information at this point to be able to solve this by hand. But what we will do is we're going to just plain and simply get the calculator out, and we'll go to our integral right here, and we're going to go from 1 up to 8, and then we'll say, here's your square root of 1 plus. Now, it's up to you whether you want to do what's known as pretty print. I mean, you could, and I think when kids have this version of the 89 or the 84, pardon me, they'll tend to want to do that, and that's fine. You can use the alpha y equals to get the fraction to look that way. But you don't have to. But look, that's pretty much all you got to do except to hit a dx. You hit enter, and you will get 7.289. That is your arc length. Like we said, if the curve could be thought of as the rope that was laid on the curve, that would be the length of the rope when you'd stretch it out, right? So that's pretty cool that you can actually find that. Now, what Kunj was asking a moment ago, and this is our last problem, he was saying, hey, what if, all right, so guys, what if your equation that they're giving you actually is way easier to be expressed as x equals something? And that can and will happen. And, then you'd look at your points. You could say that, I could have g of c and g of d to d. It's the exact same formula, except you're integrating with respect to y. So that's your last problem. First of all, looking at number 2, I think you can see that what's happening is you're going to have a hard time solving for y. That's just not going to happen. Instead, look what happens when I solve for x. And that, by the way, you're going to see on quite a bit of the homework. Look, it's way easier to get x alone. I'm going to divide everything by a 30y cubed. Everything gets divided by 30y cubed. And then all of a sudden you could say, well, I've got x is equal to, well, this is y to the 5th over 30. And this you could say 15 over 30 is a half, but then we'll say y to the negative third. Right? Now, look, I guess what I want to say is I can now go ahead and find out what g prime of y is. If, g of y is this function right here, I can take the derivative with respect to y. You can see quickly when I bring down the 5 over the 30 would get you a 6. You'd have y to the 4th. Bring down a negative 3, you'd get negative 3 over 2. Careful, y to the negative 4. That is one of the bigger mistakes. Please be careful with that. Easy to mess that up. But look, I guess what I'm trying to get you to see is right now you're trying to find the arc length where the roles of x and y have been reversed. You're now integrating with respect really to y instead of x. So what are you really going to have to type in? You're going to go from 1 to 2, my beginning y value, to my ending y value. I'm going to have the square root of 1 plus, and then I'm going to have to type this thing in here, and just remember to square it, right? Squaring, if you don't square it, guys, that's the other big common mistake. What do you do now? Plain and simple. You just go ahead and you got to get this thing typed out. Now, again, all you got to do is hit math, get that integral back up, and kids will ask sometimes, so should I be typing in y's instead of x's? You certainly may. You're always welcome to do that, but I do want to point out to you that it's just as well to just, even though you know that you're integrating with respect to y, it's probably just as easy to just momentarily just say, look, x is so much easier to get this out. So I'm going to go ahead and type in a 3 all over 2, and then we'll have our x, which is really a y. And then we're going to square that. And again, if you would have pressed in your y instead of x, that's fine. 1.471, and you're good.